So here, in the first chapter of, or first chapter of the first section of the derivatives chapter, section 3.1, there is an important distinction, and that's between the average rate of change of a function on a specified interval versus the instantaneous rate of change. The instantaneous rate of change always does this limit business. Okay? So the instantaneous rate of change at a point 3 is going to be the difference quotient starting at 3, taking the limit as h goes to 0.
Yeah.
Compare that to the average rate of change, where essentially you just plug in the endpoints, but it'll be easier to understand once we actually look at the example. So the function is x squared plus 2.
Mm-hmm.
If we're looking at the average rate of change on the interval 3, 3.5, then what we're going to do is we're going to, mentally you could think of it as f of 3 plus 0.5 minus f of 3 over 0.5. That's on the interval 3, 3.5. We're actually taking the endpoints and we're plugging them in to the difference quotient. Yeah. And I've just written 3.5 as 3 plus 0.5 to emphasize that it does actually follow the same pattern as 3 plus h. But in actuality, that's not the way we're going to use it. We're just going to actually do f of 3.5 minus f of 3 over 0.5. And of course, 0.5 is 3.5 minus 3. All this is the slope of the line. The secant line through the points 3, f of 3 and 3.5, f of 3.5. Okay, now we just roll up our sleeves and do it. F of 3.5 is 3.5 squared plus 2 minus f of 3 is 3 squared plus 2. All of that divided by 0.5. Okay, this is gross. I'm going to hit pause and actually multiply out 3.5 squared. Okay? And we're back. And evidently 3.5 squared is 12.25. So we have 12.25 plus 2 minus 9 plus 2, which is 11. All of that over 0.5. 14.25 minus 11, which is 3.25. And then when I'm dividing by 0.5, that's like dividing by a half, which is the same as multiplying by 2. In the end, it's 6.5. The important thing to take away from this is that when you're asked for the average rate of change, you're basically just plugging in the endpoints and doing slope the way you did slope forever and ever. The instantaneous rate of change involves a limit. Okay? Exactly. And so I'm going to move to the right, and I'm going to figure out what f prime of 3 is, which is the notation that we introduced in one of the other videos. It's going to be the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. Okay. What was this? This was limit h goes to 0 of 3 plus h squared plus 2 minus 3 squared plus 2. All of that over h. You'll recognize this is essentially the same as before we had h equal to 0.5. 3 plus h squared is 9 plus 6h plus h squared plus 2 minus 11. All of that over h. Of course, we're still writing the limit. 9, 2, and 11 cancel out. And I can factor an h out of 6h plus h squared. And now I'm ready to plug in h equals 0, and I actually get 6.
Great.
Okay, let's zoom back out and look at the whole thing all at once. We were asked to do the average rate of change.
Mm-hmm.
That means we actually plugged in the endpoints. There was no limit involved, and we got a number. And that number was 6.5. Okay? Then when I took the limit, I actually got 6. It's a little bit different from 6.5. I'm just going to draw a picture quickly of what's happening here. And the situation is this. We have a function x squared plus 2, and we are looking for the slope of the tangent line at the point, I guess, 3 comma 11. So that point would be something like this right here.
Mm-hmm.
And the difference then between the two calculations is that the first calculation actually took a second point, which was slightly further away, and found the slope that was between those 2 points. That would be the slope of a secant line.
Mm-hmm.
Whereas if I'm taking the limit as h goes to 0, you can visualize it's like this green dot is moving towards the black dot.
Yeah.
Okay? And thus we have illustrated the difference between, so I'll say the secant line, this corresponds to the average rate of change. Versus a line that only uses the point at 3 comma 11, and that would be a tangent line, which involves a limit. Okay.